Okay, welcome back. Braem again, trying to help again with the digital systems, but we're doing basics now. And we looked at base 10 previously, and I gave a few examples, one of which I had done already, but anyway, it was to catch out to whether people are sleeping or not. But then what I'm going to do next is obviously, as promised, base 2, and we're going to see how the work is similar really. So personally, I'm gonna feel like I'm repeating myself, but I know it's new for some people. So okay, let's see. Let's hope we enjoy. All right, let's then start with the base t base 2 or binary name base 2, which you already called binary by for 2. All right, so we saw how from our language, I pretended for a second that base 10 wasn't our language, and we saw how from our language we want to go to another language. We say we are encoding. So each time we're encoding, we are going to a different language from our own. What do we do to try in the number system to try and register a different system from our own? We normally divide by the base we intend to go to. All right, we try to see how many twos. We're counting in twos now, so we're going to be looking for sets of 2. The other time we're looking for sets of 10. We're dividing by 10 to see how many sets of 10 we have each time, how many sets of 10s, how many tens of 10s, how many tens of 10s of 10s, etc. Now we're going to do the same thing with base 2. We're going to look for twos, look for how many units. If we can't, what can make twos will be units. So see how many twos we have. In those twos, can you still have sets of twos that will give us fours? From those, can you have further sets of twos that will be eight, etc. So now let's start with the very number that I think I started with. I think I started with the 17. So let's say I want to convert 17 to base 2. All right, our language is, I understand 17, but I want to know what it will be in the language of twos. All right, so what do? I'll look for sets of 2. I'll say, okay, 17, do you have sets of 2? 17 will say, yes, I've got 8. We're dividing, remember, I've got 8. Remember, we're dividing by the base we're trying to go to. We pretended that base 10, we didn't know base 10 was the same as our language. So we say, let's go to base 10 that we don't know. And then we discover that, oh, we have always known base 10. Now we're going to base 2. We're going to divide by what? By 2. I think that is clear enough. So we've got aces there, we have a remainder, so it means these could not make what? Let me try and make it similar to what I did previously. Okay, so what we have here is 8 twos, okay, and we have a remainder. 2 times 8 is going to be what? 2 times 8 is going to be 16. 16 plus 1, remainder 1. That is the unit. These could not form twos. All right. So we say, do we have further sets of 2? We're counting in twos now. So we're looking to have further sets of 2s. So if we get sets of 2s, we're looking for 4s now. Why? Because 2 times 2 is 4. Let's see. Yes, we have what? 2 more here. It will give us 4. So I mean 4 with the remainder. This is for what? It can't be 2s. This has to be what? To be 4s. Previously we said 10. We said we looked for 10s, then we looked for what? For hundreds. So here we've got 4 fours. Because 4 times we looked for 4s. 4 4s. And what remains, if you divide 2 into 8, you get 4 with the remainder of 0. So if we take out the 8s from the 8, if you take out 8 from the 8, we won't have anything left. So what do we have? We have 0 2s left. Because remember, this was taken from the 2s. So there's no 2s left. All right. So we say, can you still find sets of 2 there? But when you look for sets of 2s, after looking for sets of 2s twice, we are looking for what? 2 times 2 times 2. We use the same logic. Last time we said 10 times 10 times 10. We said, okay, now we're looking for thousands. But here we're looking for 8s. Okay, so 8s. Oh, what am I doing? I am thinking and writing at the same time now. Okay, so 2 there is going to be 2. But what is this? Is 8 that we found here. Okay, what could not make 8s will be remainders, but there's nothing left. 2 times 2 is 4. Nothing was left, so there's no 4s left. Okay, now Can we find further sets of 2? We kept looking for sets of 10. This time the base is 2. So we are finding sets of 2 repeatedly until we've got nothing, until we can't find anything anymore. So, oh, what am I doing? Until I'm thinking of until we've got nothing, and I'm jumping the gun now. So we still have a set there, because 2 into 2 is 1. So that there is what? 2 times 2 times 2 times 2. So we've looked for 16s now. So this is a 16. A 16. Okay. Now, are there any 8s left? Remainder 0. 2 into 2 is 1, remainder 0. So there's no 8s left. Okay. So we still check. Can we get 32s? 2 times 2, 4 times 2, 8 times 2, 16. Now we're looking for 34. Says no. Obviously, it would be a miracle for us to be able to find what? To find 32s in what? In 17. So obviously there's no 32s here. 32s. 0 32s. So what was left? Oh, that one that was left was a 16. So that 16 is left. Remember 1, 16. Okay. Now we have to be consistent. We said when we write our numbers, we said when we're using base, base 10. Remember, I'll put a note here. Remember, with base 10, what did we do? We said let's took with the biggest number we did there was thousands. We said we have thousands. We have what? We have hundreds. Oh, what am I doing? Hundreds. We have hundreds. We have tens. We have units. But this was what? This was base 10. Okay. We looked for tens. We couldn't find, when we couldn't find tens, there were units left, same way as here. But this is not. So with base 2 now, we still have units. Okay. What could not make 2s? But we don't have 10s here because we looked for 2s. In the case of 10, we looked for 10s. Now we looked for 2s. So these here are what? Are 2s. Okay. Let me rather use numbers to avoid strange things here. All right. Let's just say a unit means 1. Okay. But these are 2s. In the place of 10s, these are 2s. In the place of what? In the place of hundreds, when we found 10s twice, here we found 2s twice. 2 times 2 is 4. So in the third column corresponds to, it was hundreds in the case of what? In the case of there's 10. In the case of 2s, we've looked for 2s twice, is what? It's 4s. And in the case of thousands, where we looked for 10s 3 times, here we've looked for 2s 3 times. That would be what? 2 times 2 times 2, which is 2 to the power of 3. So I'm coming to what? To that actually. I'm coming to, let's use the base now. 2 to the power of 0 is 1. 2 to the power of 1 is, 2 to the power of 2 is, 2 to the power of 3, and you can see it all works out. And now you can see that this is what we do. The base exponent system shows you we are now counting based on what? On 2s. All right. So now our 17 therefore, it had 16s. So we could go further and say here we have 16s. In the case of 10s, that would have been what? Tens of thousands. But here we have 16s. So 16 would have been 2 to, you can see that all that happens, that the power is increasing towards the left. Just like 10 was 10 to the 0, 10 to the 1, 10 to etc. Same happens with the 2. So I've done nothing different. All I've done is change the base. So with a number like 17, a number like 17 is a combination of 116 and 1 unit. Okay, we've got 116, 1 unit, 0 8s, 0 4s, 0 2s, and we know 16 plus 1 is indeed what? 17. Now you remember, I did an example in the previous case, 101, if I remember correctly, 101, and I also did 1011. Now, if you have to be realistic. If you look at this number, you will see 10,001. Now we have to therefore differentiate it. We have to be fair here. We cannot write two numbers that have two different values the same way. That would not make sense. That would not make mathematical and scientific sense. So what do? We try and avoid that. We indicate with a little, not optional. We indicate in the case of base 10, which is our language, there is my 17 there. I'm not even worrying about putting the little 10, even though doing it wouldn't really, we proved in the last exercise that doing it wouldn't affect anything. But in the case of any other base, you will not leave, because we do have a number that exists that is 1001, and that is base 10, and it is the number 10,001. So should you leave the little 2 there, you are basically equating 1001 we are equating that to what? To 10,001. So you have to put the little 2 to differentiate. That has to be, we have to be clear about that right now. You leave it, it means you are changing the value of the whole thing. All right, so let's look at another example. Let's take the 101, because now we did have 101. I want to prove to you that 101, if there's nothing, we know it was, we even proved by dividing by tens, it was 101 base 10. So yes, in the case of base 10, you can leave that. It's optional. It's fine, because it is our language anyway. It is, the two are the same. But then now, in the case of base 2, if you leave that, it won't make sense, because let's take 101 and say you had left that, but you meant it to be base 2. Then it means you would have been trying to say 101 base 2. Now, these two cannot be the same. Why? Let's prove it. Because we know, when you look at this number, that is units or ones, that is twos, and that is fours. So this is basically 4 plus 1, which is equal to 5. So leaving the little 2 there suggests that you are saying 101 and 5 are basically not different. That is obviously not reasonable. So let's find out what 101 without the little 2 is with the little 2. We will therefore have to, we say this is our language. So every time we are going to a language other than ours, we divide. We are trying to say our language is working in sets of 10. So putting the little 10 or leaving it is fine. But with different languages now, you have to find out the sets that you have in the what, the sets of whatever you're looking for. If it's base 2, in the sets of 2s, if it's base 8, it will work the same. It will be the sets of 8s. If it's base 16, it will be sets of 16. But then now we are looking for base what? Base 2. So we'll divide our language. We always only divide into our language when you go to a different language. So we'll say there 2 into 101 is 2 into 100 is 50. It cannot, so this is 51. This is 50 twos that we had in what, 100, and we have a remainder, however, because the one extra could not make a 2, so this is the unit. All right, then we say, do we have further twos? Having twos in sets of twos is actually finding fours. 2 by, it's like I'm dividing 101 by what? By 4. So it will give us what? 25. 2 into 101 is 20. Sorry, 4 into 101 is what? Is 25, because 4 times 25 is 100. Né? But then 2 into that will give us 50. Divide by 2 again is the same thing. So we now have 25, but these are obviously fours. Therefore, since the number goes in straight, it leaves no remainder. So once we take out the fours, we will have no twos left. Okay. Now we say, can we get 8s? Of course, 25 can give us 8s. That will be what? That will be 12. 2 times 12 is 24. So therefore, we have 12 8s. But those 12 8s will give us what? Will give us 12, if you say we've got 12 8s, but if you do that, you are going to find yourself having what? Having a remainder, because if you say 2 there, it's 1 2. remainder 1, and that 1 was a what? Was a 4. Okay, 12 times 8 is 96. 96 plus 4 is going to be what? It's going to be 100. Plus that 1 unit there is going to give us what? Our 101. So you can see it works quite similarly, quite in fact identically to the best 10 scenario. That's why I said let's understand the best 10, because it will make our life easy when you come to the other bases, 2 included. So we are still trying to find further sets. Now we are looking for 16s. 16s, they will give us a 6. These are what? 16s that we're looking for. 16s. Sweet 16s with the remainder. It went in there straight, 2 went in there straight, so the remainder of nothing, so there is no 8s left. Okay, then 2. Okay, I looked for what? You're right. So now I look further to see if I can find 32s. All right, then I find 3 of them. These are 32s. Oh, 32s. My pen is going on strike. 32s. Remainder. Now we've got 2 there, go straight with no remainder, so there's no 16s left. I'm trying to avoid writing the number 16 because it will be 016 now, it will be confusing to us. So now we say, can we find 64s? After 2 times 32 is what? 2 times that 32 is going to be 64. Yes, we can find 164. And then if you look at that now, what will it give us? It will give us 164. Okay, 164 with the remainder of 2 into 3 gives us what? 1 remainder 1. So that 1 was, we're looking among 32, so these are 32s. All right, so can we find 128? It will be a miracle to find 128 in 101. So obviously no, we cannot find any 128. Here I'll have to do this 128. Okay, 128, 0, 128. So what remained there was what? Was the 164. Okay, 164. All right, so let's look at it. When you write a number, obviously we've seen now we write the most significant digit first. So our most significant digit is the 64. So it means if we put this up, we're going to have 64s followed by 32s. We keep going down by 2, by a factor of 2. We go to 16s. We go to 8. We're going down by a factor of 2. We go to 4. We go to 2. We go to 1. Okay, so those are our units. So now if we have a number like that, we know we have 164, we have 132, we have no 16s, we have no 16s, no 8s, we have 14, we have no 2s, and we have 1 unit. Okay, so that there must have a little 2, and then we say, look, if we look at it, this is the same. If we sum those up, we've got 1 times 64 plus 32 plus 4 plus 1. 64 plus 32 is obviously 96. 96 plus 4 is 100. 100 plus 1 comes back to our what? Our 101. Wow! We need to give ourselves a round of applause. That was nice and easy. So how do we get the thing? So is it necessary to keep writing 2s? We know we're looking for 2s. We know what's left is units. So we need to get to a point where we understand this and we don't have to keep doing it all the time. So I'll take my rubber and I'll say, this does not look very neat. So what will I do? I will simply go with the rubber and say, can you please remove all this junk here? All right, not that is wrong, that is too tedious, too much writing, so we try to avoid that because it will take us forever. All we do is just use our we just use our answers and remainder. So 2 into that was that remainder 1. There's no remainder here. There is a remainder 1 there. There is what call this? No remainder here. 6 times 12. 6 times 2 is 12. No remainder. Okay. Again, 2 into that will be 3. 2 into 6 will be 3 with no remainder. 2 into 3 will be 1 with a remainder of 1. And 2 into 1 will be 0 with a remainder of 1. And we remember that this is our unit. This is our what? Our 64. We take our answer up. Why? Because we take it from the what? We take it from the most significant digit to the least significant digit. This was 2. We had units. This is so after so much. So this is so much more weight. This is more significant than that. So we take our answer from. This is our MSD, most significant digit. This is our LSD, least significant digit. Just like here, 64 is what? Our MSD, and this is our LSD. Alright, so you understand now why we must take it up. I don't think that was that difficult, but I hope that it helps with what? With the, now you can see it's not really different from the best 10 stories. The bases are the ones that have changed. So now what I'll do is, we have seen how to go from best 10 or our language to a different language, in this case best 2, simply by what? Dividing by the language you're going to, the best system that we're going to. Now how do we go back? This is what we do to go back. By the way, are we allowed to say, okay, let me show you a much faster and much easier way of doing this, which is still allowed. If I have 100, okay, I put 101, okay, I could have said, okay, 101. I know that I don't have 128s here. I know that the next one is 64s. I know that the next one is what? Do I have 64s there? There's 1. As long as the number is bigger, I know I can take out that. Okay, I take out my biggest one. I take out my most significant first. So when I take out 64 from 101, what do I have left? I actually have what? 37 left. Ne? Because 36 and 64 give us 100 plus that extra one, we've got 37 left. So I say, okay, the next one I'm going down in factors of 2. So this is 32. Do I have 32 in what's left? Yes, because it's a 37. So I have, yes. Now, what's next? The next is a 16. But after taking out 32 from 37, what do I have left? I've got only 5 left. So can I take 16 from 5? No. What's next? The next factor is 8. Because remember, it's going down in factors of what? In factors of 2. So I'm going to 8. So can I take 8? I've got 5 left. Can I take 8? No way. It has to be a miracle. Okay. So now I then go further and I say, with a factor of 2, factor down with 2, I go to 4. Can I take 4 from 5? Definitely. Alright. So what do I have left after take 4 from 5? I only have 1 left. So however, I still have 2. Can I take 2 from 1? How come? No way. So I've got what call this 1. So I couldn't take 2. Then the last one, is the what? Factor of 2 again will give us 1 there. Now can I take out 1 from 1? Yes. Am I done? Yes. I've taken everything. So therefore you can see how 101 cannot be left as 101. This is 1,100,101. It will be a miracle to say that 101 is equal to that. No, I will mark this wrong. So you have to show us that you know 1,1,0,0,101 only with the best 2. Only if it's in best 2 can it be equal to what? Can it be equal to 100 and you get a full mark. But if you suggest to us that 101 is equal to 1,100,101, you will see your marks fly, and you try and keep as many marks as possible. So you need to be very careful about some of these little nitty-gritties, what we call nitty-gritties. Okay, so how it is only fair that we handled an example. Before I go to these examples with commas, it's also fair, even though I've done it already, but I want to bring this to particular attention. If we had a number. We have a number and we are going to a base we don't know. In this case 2. We are going to base 2. We don't know that language. Our language, we divide. So we divide by 2s and we take our remainders. MSD is the last one we get. So going up, we understand this part. Now, what if we want to go back to our number? We have a number in base 2 and we want to go back. We simply we use the weight system. We've already done it here. So I'm saying we have already done it. That's what we're doing here. We're already doing it here. All we do is say in that that number has a weight of 64. That number has a weight of 32. I don't care about zeros. That one has a weight of 4. That one has a weight of what? Is a weight of what? Of 1. So I just add them up and I will get my answer. But sometimes it's easier to just say I have the number 1 0. Oh, so it's 1 1 0 0 1 0 1. Of course, with the little 2. Okay. If you say to me, if you don't include the little 2, and you say I must give you this number in base 10, I'll write it as it is, because that's what it is. If it doesn't have a little base, it is what it is. It is base 10. So, but if it has a little 2, or you tell me it's in base 2, and then you say I must change that to base 10, our language, I'm now going to decipher. I'm now going to do what is called decode. So if I have to come to base 10, I'm coming to our language, so I'm decoding. So I will say, oh, okay, but I know that 1 1 0 0 1 0 1, this stands in the what? This stands in the space of the unit. That stands in the space of the 2s. That stands in the space of the what? Of the 4s. That stands in the space of the what? 8s. 16s. That stands in the space of the 32s. And that stands in the space of what? Of the 64s. But I also know that with the base exponent system, this is 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power of 2, this is 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. So I could either use it, do it like that, like we've already done it like that, or I could say my number that is equal to 1 times 2 to the power of 6 plus 1 times 2 to the power of 5 plus 1 times 2 to the power of 2 plus 1 times 2 to the power of 0. Remember, all I wrote here was the exponents, okay? I wrote only the exponents. I didn't write 2 to the power of 2 to the power of, I just wrote the exponents, okay? So, you can see I only worried about where I had ones, because the other space was going to be 0 times what? 0 times whatever. It was all going to give me zeros. So this here is going to be the same as our 64 plus 32, giving us a nice 96, plus our 4, giving us a 100, plus our 1, giving us 101. So this is how I would come back. This is how I go to it. This is how I come back. I use the base exponent system to what? To come back to our language. I use divide to go away from base 10, which is our language. Okay. So I don't know. I don't think that is difficult. Maybe a few examples and practice. You know, practice makes perfect. So maybe a few examples will assist. All right. So what I want to do, I want to also engage a few examples that have commas. Okay. Because we've done commas in what? In base 10, it's only fair that we do commas here. However, I would like to highlight something before I go there. Let me take this out. All of it. Oh, what am I doing? I meant to use my eraser. Let me take all this out. Let me take all this out. And then what I want to do is I want to put a few notes here. Oh, why am I think my I'm a little bit skew. Let's take a few notes here. Okay. We started with base 10, ne? So let's say base rules. I'll say base rules. Okay. Rule number 1. Okay. Remember base 10 with the what, the symbols 0, 1, 2, 3, all the way up to 9. 1 to 9 is 9, obviously. With the 0 it makes it 10, so we had 10 symbols. You saw now in base 2 we only did what, 0 and 1. Okay, obviously we couldn't have 2 because every time we look for a set of 2, that 2 what will be taken away. So what did you realize? We've got the number of symbols. There were 10 for base 10. Number of symbols. There were 10 for base 10, and there were 2 for base 2. You will see, I can't use the rule of induction yet because we haven't done a third random case. But let's say now, number of symbols so far you've seen, and you will continue to see. I just want to mention this because sometimes we tend to get carried away and think we've mentioned it already when we've forgotten to mention it. So number of symbols is the same as the base. Okay, it's the same. So you can rest assured now, same as the base. You can rest assured now that base 8 will have 8 symbols. Okay, the same as the base. All right, and then biggest symbol. Biggest symbol, you saw how 9, which is 10 minus 1, 1, which is 2 minus 1. Biggest symbols, the biggest symbol is what? Is 1 less, is always 1 less than the base. Okay, the biggest symbol is what they will have failed to make. Okay, because remember, if we have 1 extra, we are going to have a what? We are going to have a set. Okay, so we're going to promote and say we have an extra 1 set. So every time the biggest symbol is going to be what? The biggest symbol is going to be 1 less than the base. So what am I saying? Okay, number of symbols is the same as the base. So number of symbols equals to base. Okay, here biggest symbol, the biggest symbol, I will not write symbol, biggest symbol is equal to base minus 1. Okay, so these are the two. You must note this and don't forget this, please. Okay, I want to get that out of the way because if sometimes we get carried away in doing things and we get so absorbed that we end up forgetting to highlight this. Where we highlight, we will have seen it. Some of you are clever enough to have noticed it, but we would like to highlight it. Okay, so now that that's out of the way, I can do probably a couple of examples in base 2 using what? With decimals, with commas. Let's look at a number like 5, 125, which I believe we did in what? In the previous scenario. Let's say whether there's a little 10, we saw that base 10 and our normal language, there's no difference. So whether there's a little 10 or not, it means the same thing. That let's convert it to what? To base 2. Okay, we said we divide here and we multiply here. We divide here and take remainders up. We multiply here and take what? Why do we take what call this remainders up? I've already explained that it's because we get what? The further we go, the further we get our what? Our most significant digit. But remember, that's not the case. If we look, let me write a number. Let me take this number. If you look at this number here, with let's say it was a 15. I'll come back to our example. Let's say it was a 15 or 215. Okay, we know that we get our what? Our most significant further to the what? To the further away from our what? From our comma. Ne? We get our most significant digit further to the left. And in this case here with the commas, we get our what? We get our most significant digit on the what? This is interesting, but we still get our what? Our most significant digit on what? This on this space here. So it's a little bit different, but I don't know whether because obviously a tenth is way more significant than what? Than a 100th, than a 1000th. Okay, so if I lost value here, If I lose this 1 here, I've lost more than if I lose all that 5, because I will still have comma 1 2, which is not very far from comma 1 2 5, rather than if I lose comma 1, that 1, then I will have comma 0, which is way further. So our most significant is immediately after the comma, whereas in this case here, our most significant was furthest from the comma. So you can see now that it will explain now why rules are going to change. You will see now our rules are going to be different for that specific reason. Let me go on now and entertain our example, hoping that what I just said now will be also a little bit useful. All right, let's take the 5. We'll divide into the 5 because we've seen how we did with base 10, that we still do it the same way. The whole number will still treat it the same way we've done all this time. So 2 into 5 there will be 2 with a remainder of 1. Now I'm saying 2 2s with a remainder of 1 unit. So we remember our unit is the first one, so we're going to take things towards the the unit. We're going to say, do we have 4s? Yes, we have 4s, because 2 into 2 is 1. Yes, there's a 4 in 5. So all right, this will say remainder 0, because once we take that 2 in there, there will be nothing left. So we say, do we still have sets of 2s? No, so we know we're done. Remainder 1. And then we take, even though the number looks the same down and up, but rest assured this is our 4, and that is our remember, we found 2 2s, we found 1 4, and we couldn't find an 8, so the remainder was a 4. So this is our 4. So sometimes numbers don't look the same, so it's very careful to indicate that you're going to take your number up. Regardless of it, you have to show us that, regardless of it looking the same, you have to show us that you know that the least significant is the one at the bottom, and the most significant is the one at the bottom, and the least is the one at the top. So our number therefore says our 5 is equal to 101. I was going to put a little 2, but I'm not done. I'm still going to do the decimal part. So what am I going to do? 0,125 times the base. We divide by the base and we multiply by the base. So that time we were taking remainders. This time we're going to take carries. We keep the number of decimals the same. There is a scenario where last time I just jumped and said 250 because my head was already on base 2. So let's multiply now. This is going to be 250. This time I'm right. But 250 came from what? From the 3 decimals. So we carried nothing. Okay. Then we go on and say multiply again by 2. And this is going to be 500. And still I carried nothing. Now when I multiply by 2, however, what do I get? I get 1000. To keep the 3 decimal places, the 1 has to come over. So now I have what? I have 001. Remember, the least significant from the comma, the most significant is the closest. So you go towards the least significant. So what is our answer now? Therefore, our 5,125. Oh, what did I do? Okay, I can say our 5,125, our 5,125, the 5 part is the 101, the 125 part is 001, 001 with a little 2. Okay, so obviously you have to show us that you know this, because it's very easy for someone to say 100. In which case they'll be wrong because they've taken the least significant first. Okay, in this case the furthest you go from the comma, the least significant, the furthest you get, the least significant you get. Now let's prove that this is true. We said, okay, prove. Oh, why am I putting this one? This is not an abbreviation. Okay, anyway, proof. Ignore that. Proof 101, 001 with a little 2, because otherwise it's 101, 101,001, which is not what it is. This is 101,001, which is the same as 5, but let's prove it. This is the same as 5,125, but let's prove it. We know that 101, 0, 0, 1 with a little 2. This is the same as 2 to the power, I'm on 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. And obviously, common sense says we are ascending that way, we must be descending to the right. Minus 1, minus 2, minus 3. Okay, so now let's look. We have therefore there we have got 1 times 2 to the power of 2. I ignore zeros, you can use them if you want, no harm. You will say 0 times 2 to the power of 1, if that's okay with you, plus 1 times 2 to the power of 0, plus 0 times that, plus 0 times that, plus 1 times 2 to the minus 3. This here, we are happy. This is 4 plus 1 times 1, 1, plus this is the same as 1 over 2 to the power of 3, which we all know is 8. Now, if we divide 8 there, it will be 0, comma, into 10, it will be 1, remainder 2 into 20, it will be 2, remainder 2 times 8 is 16, so remainder 4 into 40, it will be 8 times 5 gives us 40. So you can see that 1/8 actually gives us what call this 0.125. So our answer therefore is clearly 4 plus 1, 5, plus that fraction part 1, 2, 5. If they said or we left it, it will still be the same. That's a footnote, so it should be a much smaller number. Like, all right, so I hope this is clear. This is one example with a comma, but I don't think one example is good enough. So let me do a second example. As an example, let's take a number like 11. Let's take a number like 11, comma 75. Let's change that to base 2. We remember from base 10, we divide when we are moving from our language to a language we don't know. So we divide by the new base, that will be base 2. So we say 2 into the whole number part, that's 11. That will give us 5 with a remainder of 1. 10 plus 1 is 11. 2 there will give us what? Will give us 2 with a remainder of 1. 4 times 2 will give us what? Will give us 4 times 2 will give us what? And 8. You will see later this is 3 plus 3 is 11, but we'll come to that. So you can keep checking yourself as you go. The more practice you have, the easier it will be to see if you are right or wrong. 2 there is will be 1, remainder 0, and 2 there will be 0, remainder 1. So we see now it will be wrong to say 1, 1, 0, 1. We have to take it up. So to know that, let's say the answer was 1, 0, 0, 1. We wouldn't know whether you took it up or down. So please indicate with the arrow when you mark. We check that you knew exactly that you're supposed to go up. So this will be, it will mean that our 11 is equal to, 1, 0, 1, 1 with a little 2, but I'm still busy, so I'll come to that. So then let's look at the decimal part, the comma part. That will be 0.75. This case, we divided that side with the whole number, we multiplied this side. We took remainders this side, we take carries this side. Now this is 75. If we multiply, what I do here, times 2, don't know what I did. I should have put my C there, but it's fine. Alright, let me make it, because if I'm not clear, then my students can't be clear. So now let me make it a little bit I like to be neat. So times 2, and I take my carries. So that will be 75 times 2, that is 150. we want the 2, so the 50 is the 2. Now we multiply only the decimal part, so it will give us what we call 100. So 1, you can multiply times 2 to start giving you zeros. So once you've got zeros, you know you're done. We know, look, this is the same, so we won't know what you'd have done if it was different. So you indicate to us that furthest from the comma was what? Was less significant. All right, so you then come there and say 1, 1, and then now our 0.75 part is the same as our 0.11 with the little 2. Okay, so that is a second example. I think it sounds so easy coming from best 10 and having shown people how to handle this in best 10. So I don't know whether there's any confusion in going back. All right, prove it. Prove. This time we'll do it right. No little dot to say it's not an abbreviation. So in proof we say, but we are saying is 1011, comma 11 base 2. What is it? 1011, comma 11 base 2. We know this is 2 to the power of 0. Therefore, this must be 2 to the power minus 1. This must be 2 to the power minus 2. This must be 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So what do we know? We know we have 1 times 2 to the power of 3. I don't do zeros. I know I've got 1 times 2 to the power of 1. You know we've got 1 times 2 to the power of 0. We know we've got, I think I'm running out of space here, 1 times 2 to the power of minus 1, and 1 times 2 to the minus 2. This will give me 8. This will give me 2. Oh, do not mistake this with the top part. Do not mistake this with the top part. That was our answer there. Okay, 8. That will give us 2. That will give us 1. That will give us 0.5 is half. That will give us 0.25 is a quarter. Alright, and you can see that this is 8 plus 2, which is 10, plus 1, which is 11. I was trying to run out because once I get here, I cannot write. So this bar here stops me from writing, so I'm trying to squeeze it in, comma, 0.5 and what? 0.5 and 0.25, you can see that 5 and 2 will give us 7, 5. So there we started off with 11.75 and we end with 11.75. Alright, so I hope this was, having come from best 10, I hope this was what? This was nice and easy. I hope we didn't do anything that was what to call this, probably seen as difficult. So let me ask you to do a couple of examples. Maybe I'll just give you 3 examples because I believe this is becoming too monotonous. So I'll give you an exercise. I'll call it 2. Ne? Alright, convert to binary and prove. (2.1) 15, 125. 2.2 27, 625. 2.3, let's say 101, let me make it easy because I've already given you too much work here. Alright, these are our what? Our 3 that I'd like you to try on your own and see if we get you understood our work. That was best 2 for you. We had best 10, we had best 2. All we've done here is conversions. We're going to come to the arithmetic of it. We're going to come to the binary arithmetic. But for now, all I want you to do is what? Get acquainted with the what? with the bases themselves. Ne? So I think for today I've done enough, or rather for this session we've done enough. So see you in the next session. Salute. Thank you so much. Hope you enjoyed.